On July 1st, 2025, astronomers discovered something that shouldn't exist. Not according to our models, not according to our understanding of how the universe works, and definitely not according to the odds. They found 3I divided by Atlas, the third confirmed interstellar visitor ever recorded. And this thing is tearing the scientific community apart in ways we've never seen before. Because here's what nobody's talking about. This isn't just another comet passing through. This is an object that defies 7 different categories of our understanding simultaneously. 7 separate, impossible things all wrapped into one cosmic visitor. And with each new observation, instead of getting clearer answers, scientists are getting more confused, more divided, more frustrated. Some of the world's top astrophysicists are now openly calling each other's work insulting. NASA and Harvard researchers are in direct opposition. And one scientist has calculated there's a 30 to 40% chance this thing isn't entirely natural. So, what's really going on with 3I divided by Atlas? Why are theories spiraling so wildly out of control? And what does it mean when our best minds can't agree on what they're actually looking at? Let's break down every single anomaly, every statistical impossibility, and every reason why this cosmic visitor has become the most controversial object in modern astronomy. What we're actually looking at. Before we dive into why everyone's losing their minds over this thing, you need to understand what interstellar objects actually are, because most people think all comets and asteroids are basically the same. They're not. Every comet you've ever heard about, every asteroid that's ever threatened Earth, every space rock that's ever streaked across our sky, they all come from our solar system. They were born here. They orbit our sunday. They're part of our cosmic neighborhood. But interstellar objects are different. These things come from other star systems. They traveled through the void between stars for millions or billions of years. They're visitors from alien solar systems that were ejected from their home worlds and sent wandering through the galaxy. We've only confirmed 3 of them, ever. The first one was ʻOumuamua back in 2017. That weird cigar-shaped object that behaves so strangely some people thought it might be an alien probe. It measured just 0.2 kilometers across, tiny. And it flew through our solar system so fast we barely got any data on it before it vanished back into deep space. The second was 2I Borisov in 2019. This one was more normal. It looked like a comet. It acted like a comet. It was about 1 kilometer in diameter. Scientists were relieved because it behaved exactly like they expected an interstellar comet should behave. Then 3I divided by Atlas showed up, and it broke everything. This thing is massive. Recent calculations show it has a mass exceeding 33 billion tons. The nucleus, the core of this object, is over 3.1 miles in diameter. That's 5 kilometers. To put that in perspective, that makes it 15 times larger than ʻOumuamua and 3 times larger than Borisov. And here's where it gets weird right away. Based on the math, based on the limited reservoir of heavy elements in the galaxy, based on the detection rates we should be seeing, scientists calculated that we should have discovered around 100,000 interstellar objects on the scale of ʻOumuamua before we ever found something as massive as 3I divided by Atlas. 100,000 smaller objects first. But we only found 2. That's like flipping a coin twice, getting tails both times, and then on your third flip, the coin lands on its edge and stays there. The probability doesn't make sense. Harvard astrophysicist Avi Loeb put it directly. Given how rare these massive objects should be compared to smaller ones, finding 3I divided by Atlas this early is statistically bizarre. It's the kind of thing that makes scientists start questioning their models, or questioning what they're actually looking at. But that's just the size problem. That's just anomaly number 1. And we've got 6 more to go. The water that shouldn't be there. Let's talk about what happened when NASA pointed the Neil Gehrels Swift Observatory at 3 I divided by Atlas. Because this is where things started getting really strange. The observatory detected water vapor, lots of it, about 40 kilograms per second pouring off this object. To give you a sense of scale, NASA scientists described it as equivalent to a fire hose running at full blast, continuously. Now, you might think, okay, comets have water ice. They release water vapor when they get close to the Sunday. What's the big deal? The big deal is distance. 3 I divided by Atlas was releasing this massive amount of water at nearly 3 astronomical units from the Sunday. For reference, 1 astronomical unit is the distance from Earth to the Sunday. So this thing was almost 3 times farther from the sun than we are. At that distance, comets don't do this. The sun's heat isn't strong enough to sublimate water ice at that rate. Normal solar system comets don't start releasing significant water until they get much, much closer. Usually inside the orbit of Mars at around 1.5 astronomical units. But 3 I divided by Atlas was spewing water like crazy at almost double that distance. The spectroscopic analysis showed something else too. Hydroxyl emissions in ultraviolet wavelengths. These emissions indicated that at least 8% of the comet's surface was actively releasing material. Normal solar system comets typically show about 3 to 5% active surface area. 8% is abnormally high, especially at that distance from the Sunday. So scientists had to come up with explanations. The leading theory is that microscopic ice grains are somehow being ejected from the surface into space where they then sublimate. But that raises more questions. What mechanism is ejecting them? Why is this happening so far from the sun? What kind of internal structure would cause this? Nobody has a complete answer. We've never seen an interstellar object behave this way. We've never seen any comet behave exactly this way at this distance. This is the kind of observation that makes researchers go back to their models and realize those models might be missing something fundamental about how interstellar comets work, or about what 3 I divided by Atlas actually is. The nickel mystery that defies physics. Here's where 3 I divided by Atlas goes from unusual to genuinely perplexing. When scientists analyzed the spectroscopic data from the Very Large Telescope in Chile, they found something that shouldn't exist in nature. The comet was emitting atomic nickel vapor, but almost no iron. In every natural environment we know of in the universe, nickel and iron are coupled together. They're created together in supernova explosions. They stay together in meteorites. They appear together in asteroids. They're found together in every comet we've ever studied from our solar system. The ratio between them is usually consistent because they form through the same processes. They have similar chemical properties. They bond together in cosmic materials. But 3 I divided by Atlas had nickel without iron, at least not in the proportions we'd expect. The European Southern Observatory tracked the emissions as the object moved from 3.14 astronomical units down to 2.14 astronomical units from the Sunday. Throughout that entire approach, nickel remained consistently detectable. Iron only showed up once the comet got within 2.64 astronomical units. That differential appearance created a puzzle. Why would nickel appear first and iron appear later? Why were they separated at all? The explanation scientists came up with involves organometallic compounds, specifically nickel tetracarbonyl and iron pentacarbonyl. These are molecules where nickel or iron atoms are bonded with carbon monoxide groups. The key thing about these compounds is they sublimate at different temperatures. Nickel tetracarbonyl turns from solid to gas at a lower temperature than iron pentacarbonyl. So, as the comet approached the sun and warmed up, the nickel compound would vaporize first, releasing nickel vapor. Then, as it got warmer, the iron compound would vaporize, releasing iron vapor. That explains the observation, technically. But here's the problem. Organometallic compounds like nickel tetracarbonyl and iron pentacarbonyl aren't commonly found in natural cosmic environments. Nickel tetracarbonyl specifically is something we associate with industrial refining processes on Earth. It's used to purify nickel metal. Finding it in a comet is extremely unusual. Finding it in an interstellar comet is unprecedented. Some researchers have described this as an extreme abundance ratio that defies conventional astrophysical processes. Others have started using phrases like industrial-style refining when discussing the chemical signatures, and that kind of language, even if it's meant as a technical description, immediately triggers speculation. Because if you're using words associated with artificial processes to describe a supposedly natural object, people start asking uncomfortable questions. Is there a natural process that could create these organometallic compounds in a comet? Maybe. We don't fully understand the chemistry of the molecular clouds where comets form in other star systems. Different stellar environments might produce different chemical signatures, but we don't know. We've never seen this before. And the decoupling of nickel and iron remains one of the most cited anomalies when people argue that 3I divided by Atlas might not be entirely natural. Carbon chemistry that makes no sense. The James Webb Space Telescope observations of 3I divided by Atlas revealed another chemical impossibility. And this one might be even stranger than the nickel-iron problem. When Webb analyzed the composition of the coma, the cloud of gas and dust surrounding the nucleus, it found that 95% was carbon dioxide, only 5% was water, and almost no carbon monoxide. Read that again. 95% carbon dioxide, 5% water. Every comet we've ever studied from our solar system is dominated by water ice. Water is the primary volatile component. Carbon dioxide is present, but usually as a minor constituent. And carbon monoxide is typically detected in significant amounts. The ratio between carbon dioxide and water in 3I divided by Atlas is 7.6 to 1. That ratio ranks among the highest ever measured in any comet, ever. Even Borisov, the previous interstellar comet, had a much more normal composition. It looked like solar system comets chemically, which made sense because comets should form through similar processes regardless of which star system they're born in. But 3I divided by Atlas is completely different. Its chemistry doesn't match solar system comets. It doesn't match Borisov. It doesn't match any theoretical models of how comets should form in protoplanetary disks around other stars. The depletion of carbon monoxide is particularly strange. In the cold molecular clouds where comets form, carbon monoxide should be abundant. It should be incorporated into the ice as the comet accretes material, but it's essentially absent from 3I divided by Atlas. Scientists have proposed various explanations. Maybe the comet formed in an unusually warm region of its protoplanetary disk where carbon monoxide couldn't condense. Maybe it underwent some kind of thermal processing that drove off the carbon monoxide but retained the carbon dioxide. But every explanation requires special conditions, unusual circumstances, things that should be rare. And when you need to invoke special circumstances to explain one anomaly, and then different special circumstances to explain another anomaly, and then more special circumstances for a third anomaly, At some point, you have to start wondering if maybe the simplest explanation is that this object is genuinely unusual in some fundamental way. The carbon chemistry of 3I divided by Atlas doesn't fit our models. It suggests formation conditions or processing history unlike anything we've seen before. And combined with all the other anomalies, it adds to this growing sense that we're looking at something that doesn't quite belong in any category we have. The trajectory that's too perfect. Now let's talk about where 3I divided by Atlas is going. Because this is where things start feeling less like science and more like a cosmic mystery novel. The object's trajectory brings it suspiciously close to multiple planets in our solar system. Close approaches to Venus, to Mars, to Jupiter. Scientists calculated the probability of a random interstellar object passing close to all 3 of these planets on a single trajectory. The odds came out to less than 0.005%. That's 5 in 100,000. Essentially, if you threw a dart at a map of the solar system from interstellar space, the chances of randomly hitting a path that takes you near Venus, Mars, and Jupiter are basically 0. But that's exactly the path 3I divided by Atlas is following. The orbital inclination adds another layer to this. 3I divided by Atlas has a retrograde orbit, meaning it's moving opposite to the direction most objects in our solar system orbit. But here's the thing, its inclination is only 5 degrees relative to the solar system's ecliptic plane. The ecliptic plane is like the main highway of the solar system. It's where all the planets orbit. Most comets and asteroids from our solar system stick relatively close to this plane, because they all formed from the same rotating disk of material. But interstellar objects should come from random directions. They've been wandering through the galaxy. There's no reason for them to be aligned with our solar system's plane. They should come in at all kinds of crazy angles. Yet, 3I divided by Atlas is only tilted 5 degrees. It's essentially sliding along the solar system's equator. That alignment allows it to access the inner solar system with minimal energy expenditure. It's the most efficient trajectory possible for visiting multiple planets. Loeb and his colleagues published a paper discussing this. They pointed out that if you were designing a trajectory for a hypothetical spacecraft to explore our solar system, this is almost exactly what you'd choose. It's a path that enables what's called a reverse solar O-berth maneuver. That's a theoretical spacecraft braking technique. You use the sun's gravity to decelerate efficiently. If you wanted to slow down enough to stay in the solar system instead of flying straight through, this kind of trajectory would let you do that with minimal fuel. Now, to be clear, Loeb and his team didn't say this proves 3I divided by Atlas is artificial. They were exploring possibilities, running calculations, showing what the math says about the trajectory. But the math says the trajectory is almost impossibly convenient if you're trying to survey multiple planets. And that's uncomfortable, because it means either we've witnessed a 1 in 20,000 coincidence, or there's something about this object's origin or purpose that explains the alignment. Some researchers have connected this to what's called the dark forest hypothesis. It's an idea from Lou Sixon's science fiction novel about why we haven't detected alien civilizations. The hypothesis suggests that alien species stay hidden because the universe is dangerous. Any civilization that reveals itself might be destroyed by more advanced civilizations. Under this framework, if an alien civilization wanted to study our solar system, they'd send a probe disguised as a natural object, something that looks like a comet so it doesn't trigger alarms. And they'd choose a trajectory that allows efficient observation of multiple planets while maintaining the cover of a random interstellar visitor. Is that what's happening? Almost certainly not. The dark forest hypothesis is speculative fiction, not established science, and invoking alien probes to explain astronomical observations requires extraordinary evidence. But the trajectory is real. The statistical improbability is real. And when combined with all the other anomalies we've been discussing, it contributes to this mounting pile of coincidences that don't quite add up. The WOW signal connection. Here's where things get truly bizarre. In 1977, a radio telescope at Ohio State University detected a strong narrowband radio signal. It lasted 72 seconds. It appeared to come from the direction of the constellation Sagittarius. And it was so unusual, so unlike anything they'd seen before, that the astronomer who discovered it wrote, "Wow," on the printout. The WOW signal has never been detected again. Nobody knows what caused it. For decades, it's been one of the great mysteries of radio astronomy. Every attempt to find it again has failed. Now, here's what Avi Loeb calculated about 3I divided by Atlas. In 1977, when the WOW signal was detected, 3I divided by Atlas was positioned approximately 600 astronomical units away from our solar system. That's 600 times the distance from Earth to the Sunday, way out in the outer reaches beyond the Kuiper Belt. And the celestial coordinates of where 3I divided by Atlas was located at that time were separated by only 9 degrees from the direction the WOW signal appeared to come from. The probability of that alignment happening by random chance is roughly 0.6%. Now, Loeb was careful to present this as an interesting coincidence, not proof of anything. But he ran the numbers on what it would take if 3I divided by Atlas actually transmitted the WOW signal. At a distance of 600 AU, to produce a signal strong enough to be detected on Earth, you'd need a transmitter generating between 0.1 and 1 gigawatt of power. That's roughly equivalent to a nuclear power plant. Could an interstellar object carry that kind of power source? If it were artificial, potentially. We're talking about technology far beyond what we have, but not beyond what's physically possible according to our understanding of physics. Is this likely? No. Is it impossible? Also no. And that's what makes the WOW signal connection so controversial. Because it takes 3I divided by Atlas from being a weird comet with unusual properties to being potentially connected to one of the most famous unexplained signals in the history of astronomy. Critics of this theory point out that the 9-degree separation is significant. That's about 18 times the width of the full moon as seen from Earth. It's not an exact match, and in the vastness of space, being off by 9 degrees is actually quite far. But supporters note that 0.6% probability isn't nothing. If this were the only unusual thing about 3I divided by Atlas, it would be dismissible as coincidence. But when you add it to the size anomaly, the water emissions, the nickel-iron decoupling, the carbon chemistry, and the trajectory coincidences, it becomes another data point in a pattern of things that individually could be explained away, but collectively start to seem very improbable. The WOW signal connection is probably the weakest of all the anomalies. It requires the most speculation. It has the least direct evidence supporting it, but it captures people's imagination because it ties 3I divided by Atlas to something that already existed in popular consciousness as a potential alien signal. And whether it's real or not, it's absolutely contributed to theories spiraling out of control around this object. Physical properties we've never seen. Beyond the chemistry and trajectory, 3I divided by Atlas displays physical characteristics that don't fit any existing category of celestial object. The most visible of these is the anti-tail, Most people know that comets have tails that point away from the sun because the solar wind and radiation pressure push the gas and dust in that direction. But 3, I divided by Atlas has been observed with a stream of particles pointing toward the Sunday. Antitails aren't completely unprecedented. They've been seen before in certain geometric configurations where it's actually an optical illusion. The tail is still pointing away from the sun, but from Earth's perspective, the angle makes it look like it's pointing toward the Sunday. But the antitail observed in 3 I divided by Atlas appears to be a genuine physical phenomenon, not a geometric projection effect. That means particles are actually moving toward the sun, which shouldn't happen under normal cometary physics. The leading explanation involves larger dust particles that aren't affected as much by radiation pressure. These particles might fall back toward the nucleus under gravity, creating a stream of material that appears to point sunward. But this is speculative. We don't have a complete physical model for what's creating this effect. Then there's the polarization measurements. Polarimetry tells us about the size, shape, and composition of dust particles in the coma based on how they scatter light. Observations using the Very Large Telescope revealed that 3 I divided by Atlas exhibits the most extreme negative polarization ever recorded for any astronomical object. It reaches a minimum polarization value of -2.77% at a phase angle of 6.4 degrees. To understand what that means, you need to know that when light scatters off dust particles, it can become polarized, meaning the light waves align in a particular direction. The degree of polarization tells us about the particles doing the scattering. Most comets show a particular polarization signature. Asteroids show a different signature. Trans-Neptunian objects and centaurs show yet another signature. Each type of object has a characteristic polarization curve. 3 I divided by Atlas doesn't fit any of them. Its polarization signature is nearly twice as extreme as any previously measured celestial body. It's so far outside the normal range that it doesn't fall into any existing category. What does that tell us? The dust particles in 3 I divided by Atlas's coma have unusual properties. Maybe they're unusually large. Maybe they have an unusual composition. Maybe they have an unusual shape or structure. Whatever the explanation, the polarization data indicates that the material making up this object is fundamentally different from anything we've studied before. Some researchers have suggested the polarization might indicate the presence of organic materials or complex molecules coating the dust particles. Others think it might indicate a different formation history, where the object accreted material in a different stellar environment with different chemical conditions. But nobody has a definitive answer. The polarization data is just one more piece that doesn't fit the puzzle we thought we were solving. An object older than our solar system. Let's talk about age, because this might be the most mind-bending aspect of 3 I divided by Atlas. When scientists ran trajectory models backward, calculating where this object came from and how long it's been traveling through space, the numbers got extreme. The Tadahai-Oxford Interstellar Object Population Model suggests 3 I divided by Atlas could be over 7.6 billion years old. Some estimates push that to 10 billion years. Our solar system is 4.6 billion years old. Earth is 4.5 billion years old. The earliest life on Earth appeared around 3.8 billion years ago. If 3 I divided by Atlas is really 10 billion years old, it was already an ancient object, wandering through space for billions of years before our sun even formed. Before Earth existed, before any planet in our solar system existed, it might have formed in the early Milky Way when the galaxy's structure and chemistry were completely different from today. The first generation of stars had just seeded the universe with heavy elements. The ratio of different elements was different. The density of the interstellar medium was different. If you could analyze the exact composition of 3i divided by Atlas's nucleus, you'd potentially be looking at a direct sample from the Milky Way's primordial era, a time capsule from when the galaxy was young. The age estimates suggest it might have originated from the boundary region between the Milky Way's thin disk and thick disk. These are different structural components of the galaxy with different stellar populations. The thick disk contains older stars with different chemical compositions. An object from that boundary region would have chemical signatures unlike anything formed in our local stellar neighborhood, which might explain some of the unusual chemistry we're seeing. But here's where it gets complicated. Age estimates for interstellar objects are inherently uncertain. They depend on assumptions about the object's velocity, its trajectory through the galaxy, and the dynamics of stellar populations. Small changes in those assumptions can produce very different age estimates. Is 3i divided by Atlas really 10 billion years old? Maybe. Could it be younger? Also maybe. The uncertainty ranges are large, but even the lower-end estimates suggest this object is ancient by any standard. And the possibility that we're observing something that predates our entire solar system, that carries information about galactic conditions from billions of years ago, is scientifically extraordinary. It's also exactly the kind of fact that fuels speculation. Because if this object has been traveling through the galaxy for 10 billion years, and it just happens to arrive in our solar system now, at a time when we have the technology to observe it, following a trajectory that takes it near multiple planets, with a chemistry that doesn't match any natural formation model we have, well, the coincidences start piling up pretty high. When scientists start fighting, here's where we need to talk about what's happening in the scientific community itself. Because the response to 3i divided by Atlas has exposed deep divisions about how science should handle genuine anomalies. NASA and ESA, the European Space Agency, have both released statements firmly rejecting artificial origin theories. Their position is that all observations of 3i divided by Atlas are consistent with a natural, albeit unusual, cometary body. They point to the spectroscopic data showing water ice, carbon dioxide, and organic compounds. All of these are expected in comets. The fact that the ratios are unusual doesn't mean the object is artificial. It just means it formed in a different environment than solar system comets. Samantha Lawler from the University of Regina represents the mainstream view. She stated that 3i divided by Atlas is most likely an ordinary comet that was ejected from another solar system. Period. Nothing mysterious about it. Daryl Seligman from Michigan State University has pointed out that there have been numerous telescopic observations showing classical signatures of cometary activity. Outgassing, dust production, a developing coma and tail, all normal comet behavior. And this is the position most astronomers hold. Yes, 3i divided by Atlas has unusual properties, but unusual doesn't mean alien. It means we're observing a comet from a different stellar environment, and we need to update our models to account for the diversity of comet formation conditions across the galaxy. That's normal science. You encounter something that doesn't fit your model. You gather more data, you refine your model. Eventually, you understand the new phenomenon and incorporate it into your theoretical framework. But then there's Avi Loeb. Loeb, a professor at Harvard and former chair of the astronomy department, has taken a very different approach. He's published multiple papers analyzing 3i divided by Atlas, and he's gone on record assigning a 30 to 40% probability that the object may not have fully natural origins. 30 to 40%. That's not saying it's definitely artificial, but it's saying there's a meaningful chance it could be. Loeb has developed what he calls the Loeb scale for measuring the likelihood that an observed object might be alien technology. It's meant to be analogous to the Trino scale for asteroid impact risks or the Richter scale for earthquakes, a quantitative framework for assessing unusual observations. But other scientists have reacted very negatively to this approach. Jason Wright from Penn State has called the scale linear and squishy compared to established scientific measures. He's criticized it as scientifically inappropriate. Other researchers have been even harsher. Some have called Loeb's claims nonsense. Others have described them as insulting to the scientific process. There's real anger in some of these responses. Why? Because Loeb's approach blurs the line between exploring possibilities and making claims. In his papers, he often frames his discussions as pedagogical exercises or thought experiments. He's saying, let's consider what the data would look like if this were artificial, and compare that to what we'd expect if it's natural. In principle, that's fine. Science should be willing to consider all possibilities, even unlikely ones, as long as they're testable. But critics argue that by assigning specific probabilities, by creating scales and frameworks, by publishing papers that get picked up by media outlets with headlines about potential alien probes, Loeb is legitimizing speculation without adequate evidence. They say he's undermining scientific discourse, that he's making it harder for the astronomy community to communicate clearly with the public about what we actually know versus what we're speculating about. And there's a deeper concern. If a Harvard professor, someone with Loeb's credentials and reputation, is saying there's a 40% chance this is alien technology, that statement carries weight. It influences how other people, including other scientists, think about the object. It shifts the Overton window of acceptable scientific discourse. Some researchers worry this is harmful, that it's pandering to public fascination with aliens at the expense of rigorous scientific standards. Others argue that Loeb is actually being admirably open-minded, that science has a tendency to dismiss anomalies too quickly. That by seriously engaging with the possibility, however unlikely, that 3I divided by Atlas might be artificial, Loeb is doing exactly what scientists should do when confronted with genuinely puzzling data. Both sides have points, and the fact that they're arguing about it so publicly, so intensely, is itself part of why theories about 3I divided by Atlas are spiraling out of control. Because when scientists disagree this strongly, when they're calling each other's work insulting or nonsense, the public sees that as evidence that something really weird is going on. If the experts can't agree, how can anyone know what to believe? The media amplification machine. Here's where things get even more complicated. Because whatever's happening in the scientific community, it's being amplified and distorted by media coverage in ways that make the controversy spiral faster. Popular media outlets love stories about potential alien technology. It drives clicks. It generates engagement. It's inherently fascinating to general audiences in a way that normal astronomical observations aren't. So when a Harvard professor publishes a paper that even tentatively explores the possibility that an interstellar object might be artificial, that becomes a headline. And headlines have to be punchy. They have to grab attention. The result is articles with titles like, "Is 3I divided by Atlas an alien mothership?" Or "Harvard scientist says Comet could be hostile alien tech." These headlines take Loeb's careful probability estimates and conditional statements and turn them into definitive claims. Readers who only see the headline come away thinking scientists believe this is probably an alien probe. They don't see the nuance, they don't see the hedging, they don't see the mainstream scientific community pushing back. This creates a feedback loop. Media attention drives public interest. Public interest drives more media coverage. Each cycle, the stories get a little more sensational. Each cycle, the speculation becomes a bit more untethered from the actual data. And here's the thing, the actual science is interesting enough on its own. An interstellar comet with unprecedented water emissions, unusual chemistry, extreme polarization, and a statistically improbable trajectory is genuinely newsworthy. That's an exciting discovery that raises real scientific questions. But that's not enough for viral content. For that, you need aliens, or doomsday scenarios, or conspiracy theories. Some outlets have published articles suggesting 3I divided by Atlas might be dropping surveillance devices near planets. Others have speculated about it being a reconnaissance probe for a larger invasion fleet. None of this is based on evidence. It's pure speculation layered on top of speculation. And the scientists doing the actual research are caught in the middle. If they push back too hard against the speculation, they risk seeming closed-minded or defensive. If they don't push back, the speculation continues to spiral. Loeb himself has defended his approach by calling his papers pedagogical exercises. He's saying, "I'm not claiming this is definitely alien technology. I'm exploring what the observations would mean if it were, as a way of thinking through the problem." That's a reasonable scientific approach. But in the context of media coverage and public discourse, that distinction gets lost. The pedagogical exercise becomes, Harvard professor says comet might be alien probe. And once that narrative is out there, it's nearly impossible to walk it back. People remember the exciting claim. They don't remember the careful hedging or the mainstream scientific consensus. This is the information cascade effect in action. One person makes a claim, others repeat it. It gets amplified and simplified with each repetition. Eventually, the claim takes on a life of its own, independent of the evidence that originally supported it. And with 3I divided by Atlas, we're seeing that cascade play out in real time. The object is genuinely unusual. That much is undeniable. But the theories about what it might be have spiraled far beyond what the data actually supports. What we'll learn soon. The good news is we're going to get much better data very soon. And that data should help resolve at least some of the questions surrounding 3I divided by Atlas. The European Space Agency's JUICE spacecraft is expected to pass relatively near 3I divided by Atlas in late 2025. JUICE is equipped with sophisticated instruments designed to study Jupiter and its moons, but it can also turn those instruments toward the comet. We'll get high-resolution images, detailed spectroscopy, measurements of the dust and gas composition at much higher precision than we have now. If there are any obvious artificial structures or components, JUICE would detect them. Then, in March 2026, NASA's Juno probe will make closer observations during 3I divided by Atlas's approach to Jupiter. Juno has cameras, spectrometers, and other instruments that can characterize the comet in unprecedented detail. These encounters are critical because they'll occur when 3I divided by Atlas is at perihelion, its closest approach to the Sunday. That's when comets typically exhibit peak activity. The outgassing increases, the coma expands, the tail becomes more prominent. If 3I divided by Atlas is a normal comet, it should behave predictably during perihelion. Increased brightness, more dust production, spectral signatures consistent with sublimating ices. If it doesn't behave that way, if it does something unexpected during its closest approach, that would be significant. It would suggest the object's activity isn't driven by solar heating in the way we expect for comets. Any deviation from normal behavior would provide strong evidence that 3I divided by Atlas is something genuinely unusual. Not necessarily artificial, but definitely not a typical comet. There's also the question of radio signals. Despite the WOW signal speculation, no systematic search for artificial transmissions from 3I divided by Atlas has been conducted yet. The object hasn't been a target for SETI observations. That's actually surprising given the attention it's received. If there's even a small possibility that 3I divided by Atlas could be transmitting, you'd think radio astronomers would point their telescopes at it just to rule it out definitively. But radio telescope time is precious. Observers need to justify their proposals, and proposing to search for alien signals from a comet that's probably natural is a tough sell. It risks being dismissed as pseudoscience or sensationalism. Still, if observations were conducted and no artificial signals detected, that would effectively kill the WOW signal connection in at least one strand of the alien technology theories. The fact that these observations haven't happened yet is itself telling. It suggests that within the professional astronomy community, most researchers don't take the artificial origin hypothesis seriously enough to dedicate resources to testing it. But over the next few months, as JUICE and Juno gather data, we'll get answers to at least some questions. We'll know more about the composition, the structure, the behavior. Whether that settles the controversy or makes it worse remains to be seen. Because here's the thing about anomalies. Sometimes more data resolves them. You find the natural explanation you were missing. The mystery disappears. But sometimes more data makes things more mysterious. You discover additional properties that don't fit. The anomaly deepens rather than resolving. If 3I divided by Atlas continues to defy explanation even with better data, the theories are going to spiral even further out of control. But if it turns out to be explicable as an unusual but natural comet, the speculation should die down. We'll find out soon enough. Regardless of what 3I divided by Atlas turns out to be, this entire episode reveals something important about how modern science handles truly anomalous observations. And it's not always pretty. Science is supposed to follow evidence wherever it leads. That's the ideal. You make observations, you form hypotheses, you test them. You update your understanding based on what the data tells you. But in practice, science is done by humans. And humans have biases, expectations, career incentives, reputations to protect. When you encounter an observation that doesn't fit your existing models, there's a natural psychological tendency to dismiss it, to assume there's an error in the measurement, to look for conventional explanations even when they require increasingly complex assumptions. This is actually healthy most of the time. The vast majority of anomalous observations turn out to have mundane explanations. Instrument errors, calibration problems, misinterpretation of data. If scientists immediately assumed every weird reading was something revolutionary, we'd waste enormous amounts of time chasing false leads. But occasionally, very occasionally, the anomaly is real. It represents something genuinely new that requires updating our theoretical frameworks. The problem is distinguishing between those two cases, between the 99.9% of anomalies that turn out to be nothing and the 0.1% that represent actual discoveries. 3I divided by Atlas sits in that uncomfortable zone. It has enough unusual properties that it can't be easily dismissed, but not enough that it definitively requires a revolutionary explanation. Every individual anomaly has potential natural explanations. The large size could just be selection bias. We got lucky and detected a rare large object early. The water emissions could indicate unusual internal structure. The nickel-iron ratio could reflect different formation chemistry. The trajectory could be coincidence. But when you pile all of those individual anomalies together in a single object, the collective improbability becomes harder to wave away. This is where you see the philosophical divide in how scientists approach the problem. One camp says we should stick with natural explanations until we have definitive evidence otherwise. Extraordinary claims require extraordinary evidence. Until we have that evidence, the default assumption should be that 3I divided by Atlas is a comet, just an unusual one. The other camp says we should seriously consider all possibilities, including unlikely ones, when confronted with multiple unexplained anomalies. If the natural explanations require stacking coincidence on top of coincidence, maybe it's worth exploring whether there's a simpler explanation we're not considering. Both approaches have merit, and in an ideal world, both would coexist productively. You'd have some researchers pursuing conventional explanations, while others explored more speculative possibilities. The different approaches would complement each other, but that's not what's happening with 3I divided by Atlas. Instead, we're seeing tribalization, researchers taking sides, personal attacks, accusations of pseudoscience on one hand, and closed-mindedness on the other. That's not productive, and it's not good for science, because the question of how to handle genuine anomalies is actually really important. It comes up repeatedly in the history of science, and the track record is mixed. Sometimes the establishment is right to dismiss anomalous claims. Remember cold fusion? Faster than light neutrinos? Both created huge controversies. Both turned out to be errors. But sometimes the anomaly is real, and the scientific establishment is too slow to accept it. Continental drift was ridiculed for decades before plate tectonics became accepted. Meteorites were dismissed as folklore before eventually being recognized as real. The challenge is that you can't know in advance which case you're dealing with. The anomaly that seems obviously wrong might be a revolutionary discovery. The anomaly that seems compelling might be a measurement error. With 3I divided by Atlas, we're watching this process play out in real time. And what's striking is how quickly the debate became polarized. How rapidly people move from here's interesting data to entrenched positions. Part of that is because of the subject matter. Anything involving potential alien technology immediately triggers strong reactions. People have pre-existing beliefs about whether alien civilizations exist and whether they'd visit our solar system. Those beliefs color how they interpret ambiguous data. If you think the universe is probably teeming with alien civilizations and we're likely being studied by them, then 3I divided by Atlas looks suspicious. All those anomalies seem like evidence of something artificial. If you think the universe is mostly empty, intelligent life is rare, and the odds of aliens happening to visit now are essentially zero, then 3I divided by Atlas looks like an unusual comet. The anomalies are just things we don't fully understand yet about interstellar object formation. Both views can cite the same data and reach opposite conclusions, because the data is genuinely ambiguous. And that ambiguity is what allows theories to spiral out of control. When the evidence doesn't clearly point in one direction, speculation fills the gap. And speculation has no natural limits. The statistical clustering problem. Here's something that doesn't get discussed enough in the media coverage. The real issue with 3I divided by Atlas isn't any single anomaly. It's the clustering of multiple anomalies in one object. Think about it this way. If you flip a coin 10 times and get 7 heads, that's slightly unusual but not remarkable. Probability says you should get 5 heads on average, but 7 is well within normal random variation. But if you flip 10 coins and 7 of them land on their edge instead of heads or tails, that's not random variation. Something weird is happening. That's the situation with 3I divided by Atlas. You have 7 distinct unusual features all present in the same object, and each one individually is low probability. The size is improbable given detection statistics. The water emission distance is unusual. The nickel-iron decoupling is unprecedented. The carbon dioxide ratio is extreme. The trajectory alignment is statistically unlikely. The WOW signal coordinates are a low probability match. The polarization signature is the most extreme ever recorded. Taken individually, you can explain each one. But together, the combined probability becomes very small. This is called the conjunction fallacy in statistics. When you require multiple independent low probability events to all occur together, the combined probability is the product of the individual probabilities. Let's do rough math. If each anomaly has a 5% chance of occurring naturally in a random interstellar object, what's the probability of all 7 occurring in the same object? 0.05 to the 7th power. That's 0.000000078125, or about 1 inch 128 millionth. Now, those aren't the real probabilities. Some of the anomalies might be more likely than 5%. Others might be less likely. And they might not all be independent. Some could be related to each other. But even if you adjust the numbers significantly, the combined probability of this many unusual features clustering in one object is extremely low. This is what bothers some researchers about the dismissive attitudes toward 3I divided by Atlas. Because while any individual anomaly can be explained away, the clustering requires explanation. Either we're witnessing an incredibly rare statistical fluke, something that happens once in 100 million interstellar objects, or there's some underlying factor that explains why these features appear together. If there's an underlying factor, that's scientifically interesting, even if it's not alien technology. Maybe it indicates a formation process we don't know about. Maybe it reveals something about the stellar environment where 3I divided by Atlas originated. Maybe it points to physics we don't fully understand about cometary activity. But identifying what that underlying factor is requires taking the anomalies seriously, not dismissing them individually without considering their collective implications. This is where Loeb's approach, controversial as it is, has some merit. By calculating probabilities and quantifying the unusualness, he's forcing the community to confront the statistical clustering rather than just explaining away individual features. Whether you agree with his conclusions or not, the mathematical exercise of asking, what's the probability of this, is valid science. It's how you determine whether something is genuinely anomalous or just perceived that way. The problem is that once you start down that road, you end up with uncomfortable conclusions. If the natural explanation requires accepting a 1 in 100 million fluke, and the artificial explanation requires accepting that alien technology exists and is visiting our solar system, which is more likely? For most scientists, the answer is still the natural explanation. Because we know natural comets exist, we've never confirmed artificial alien technology. So even a 1 in 100 million natural event is still more probable than invoking something we've never observed. But that logic only holds if you're absolutely certain alien technology doesn't exist. If you think there's even a small chance that alien civilizations exist and occasionally send probes to other star systems, then the calculation changes. This is where science bumps up against philosophy, because the question, how likely is alien technology, can't be answered purely with data. It requires assumptions about the prevalence of life in the universe, the likelihood of intelligence evolving, the probability of technological civilizations developing interstellar travel, and their motivations for exploration. All of those are massive unknowns. So different scientists making different assumptions reach different conclusions about the same data. And that's why theories spiral out of control, because there's no objective way to settle the debate with the data we currently have. Why this matters. Beyond 3, I divided by Atlas. Let's zoom out for a moment. Because the controversy around 3I divided by Atlas has implications that go far beyond one unusual comet. This is a test case for how humanity handles potential contact with extraterrestrial intelligence. Not actual confirmed contact, but the ambiguous situation where we detect something that might be artificial. And if 3I divided by Atlas is any indication, we're not handling it very well. We have scientists publicly fighting with each other, media outlets amplifying speculation over substance, the public confused about what's real and what's hype, and no clear framework for how to evaluate ambiguous evidence. This will happen again. We're discovering more interstellar objects. We're improving our observational capabilities. We're actively searching for signs of alien technology with programs like SETI and the Galileo Project. At some point, we're going to detect something else that's ambiguous. Another object or signal that has some features consistent with artificial origin, but isn't definitive proof. How will we handle it? If the 3I divided by Atlas controversy is our model, we'll handle it poorly. We'll see the same divisions, the same accusations, the same media circus. We need better frameworks for this. Not just scientific frameworks for evaluating evidence, but also social frameworks for discussing ambiguous findings publicly without immediately polarizing into hostile camps. Part of the problem is that the stakes feel enormous. If alien technology is real, that's arguably the most important discovery in human history. It changes everything about our understanding of our place in the universe. But if it's not real, if we're just seeing natural phenomena and misinterpreting them, then making a big deal about it makes scientists look foolish. It undermines public trust in science. It feeds into pseudo-scientific thinking. So both sides feel like they're protecting something important. The skeptics are protecting scientific credibility and rigor. The explorers are protecting open-mindedness and the possibility of revolutionary discovery. But that framing makes it adversarial. Us versus them. Believers versus skeptics. When really it should be all of us working together to figure out what's actually true. The 3I divided by Atlas case also highlights challenges with scientific communication in the internet age. In the past, scientific controversies played out in journals and conferences. They took years to resolve. The public rarely saw the messy process of how science actually works. Now everything is public and immediate. Papers get posted as preprints before peer review. Researchers tweet about their findings. Media outlets cover preliminary results as news. That transparency has benefits. It democratizes science. It lets people see the actual process of discovery and debate. But it also means the public sees all the uncertainty and disagreement that's normally hidden. And that can be confusing or alarming if you're expecting science to provide clear, definitive answers. Science doesn't work that way. Science is messy. It's iterative. It involves false starts and contradictory evidence and long debates before consensus emerges. With 3I divided by Atlas, we're seeing that mess in real time. And it's uncomfortable for everyone involved. The Fermi paradox connection. There's a deeper question lurking underneath all of this. The Fermi paradox. If the universe is vast and ancient, and if life and intelligence are relatively common, where is everybody? Why haven't we detected obvious signs of alien civilizations? 3 I divided by Atlas connects to this question in interesting ways. One resolution to the Fermi paradox is that alien civilizations exist, but they're subtle. They don't build Dyson spheres or broadcast obvious signals. They explore quietly, using probes disguised as natural objects, observing without interfering. If that's true, then interstellar objects like 3 I divided by Atlas are exactly where we should look for evidence. Not for obvious artificial structures, but for subtle anomalies. Things that are almost, but not quite natural. This is essentially what Loeb is arguing. He's saying the absence of obvious alien signals doesn't mean aliens don't exist. It might just mean they're being subtle. And if they're being subtle, we need to look for subtle signs. The counter-argument is that this is unfalsifiable. If you're looking for evidence that's designed to be indistinguishable from natural phenomena, then by definition you can't prove it's artificial. You can always find ambiguous features and call them suspicious. It becomes a Rorschach test. People see what they expect to see, but maybe that's where we actually are. Maybe the real answer to the Fermi paradox is that alien civilizations do exist and they are out there, but they're sophisticated enough that their activities look natural unless you examine them very carefully. In that scenario, objects like 3 I divided by Atlas would be exactly the kind of thing we should investigate thoroughly. Not because any individual object is likely to be artificial, but because the cumulative evidence across many objects might reveal patterns that natural processes wouldn't produce. This is what makes the dismissive attitudes from some scientists potentially problematic. If we assume everything is natural and don't seriously investigate anomalies, we might miss actual evidence of extraterrestrial intelligence because we're not looking carefully enough. On the other hand, if we assume everything anomalous is potentially artificial, we'll waste enormous resources chasing false leads and will never develop accurate models of natural processes. It's a genuine dilemma, and there's no easy answer. But what's clear is that 3 I divided by Atlas has forced this conversation. It's made people think seriously about what evidence of alien technology would actually look like if we encountered it. Would it be obvious or subtle? Would we recognize it immediately? Or would it be ambiguous, requiring careful analysis and debate? The fact that we're having these conversations is valuable even if 3 I divided by Atlas turns out to be completely natural. What happens next? So, where does this leave us? What should we expect in the coming months as we get more data about 3 I divided by Atlas? There are really 3 possible outcomes. Outcome 1 is that additional observations confirm 3 I divided by Atlas is a natural comet with unusual but explicable properties. The anomalies get resolved. We figure out the chemistry that explains the carbon dioxide ratio. We understand the mechanism behind the distant water emissions. We develop models that account for the polarization signature. If that happens, the controversy dies down. Loeb and his colleagues look overly speculative. The mainstream scientific view is vindicated, and we add 3 I divided by Atlas to our catalog of interesting but natural interstellar objects. The lesson learned would be that, yes, interstellar comets can have very different properties than solar system comets, and we need to update our models accordingly. But there's nothing revolutionary or paradigm shifting about it. Outcome 2 is that we get more data, and 3 I divided by Atlas becomes even more mysterious. We detect additional anomalies. The existing puzzles deepen rather than resolve. The object behaves in ways that are increasingly difficult to explain with natural processes. If that happens, the controversy intensifies. More researchers start taking the artificial origin hypothesis seriously. We get proposals for follow-up missions to study the object more closely. The debate becomes even more polarized. This would be the most uncomfortable outcome because it would leave us in prolonged uncertainty. We'd know something weird is going on, but we wouldn't have definitive answers. Outcome 3, the least likely but most dramatic, is that we detect something definitively artificial. A signal, a geometric structure, some feature that can't possibly be natural. If that happens, everything changes. It becomes the biggest news story in human history. Not just for astronomy, but for philosophy, religion, politics, everything. Proof that we're not alone in the universe. But honestly, that outcome is extremely unlikely. If 3i divided by Atlas were obviously artificial, we probably would have detected it already. The fact that it's ambiguous suggests that if there's anything unusual about it, it's subtle enough to be missed or misinterpreted. Most likely, we're headed for some version of outcome 1 or 2. Either the mystery resolves with natural explanations, or it deepens and we're left with ongoing uncertainty. What won't happen is a clean, definitive answer that satisfies everyone. That's not how science works with genuinely ambiguous data. The theories around 3i divided by Atlas spiraled out of control because the object sits right in that zone of maximum uncertainty. Weird enough to be interesting, not weird enough to be conclusive. And in that zone, human psychology takes over. We fill the uncertainty with speculation. We take sides based on our pre-existing beliefs. We fight about interpretations because the data doesn't settle the question. The bigger picture. Step back and think about what 3i divided by Atlas represents in the larger context of astronomy and our search for life beyond Earth. We're living in a unique moment in human history. For the first time ever, we have the technology to detect interstellar objects passing through our solar system, to analyze their composition, to study them in detail. Before 2017, before ʻOumuamua, we'd never confirmed a single interstellar object. The technology didn't exist. Now we've found 3. And as our observational capabilities improve, we'll find more. Each one is a sample from another star system, a piece of another world that traveled across light years to visit us. That's extraordinary. And the fact that the third one we found has all these unusual properties raises profound questions. Is this normal? Are interstellar objects typically this diverse and strange? Or did we just happen to get lucky and find an outlier? We don't know. We have a sample size of 3. You can't draw statistical conclusions from 3 data points. But 3i divided by Atlas has shown us that interstellar objects can be far weirder than we anticipated. They can have chemistry we've never seen. They can behave in ways our models don't predict. They can have properties that don't fit any existing category. That's scientifically valuable information regardless of whether 3i divided by Atlas is natural or artificial, because it tells us the universe is more diverse than our theories predicted. It means when we detect more interstellar objects in the future, we shouldn't assume they'll behave like solar system comets. We need to approach each one as potentially having novel characteristics. And maybe, just maybe, one of them will actually turn out to be artificial. It's unlikely, but it's not impossible. The universe is big, really big. There are hundreds of billions of stars in our galaxy alone. If even a tiny fraction of those stars have planets that develop technological civilizations, and if even a tiny fraction of those civilizations build interstellar probes, then space should contain artificial objects. We've never found one, but absence of evidence isn't evidence of absence. It just means we haven't looked hard enough, or we haven't recognized what we're seeing. 3I divided by Atlas might not be that first confirmed artificial object. Probably isn't. But it's made us think seriously about what we'd actually do if we encountered one, how we'd study it, how we'd evaluate the evidence, how we'd communicate about it. And it's revealed that we're not as prepared for that scenario as we thought. We don't have good protocols. We don't have consensus about what would constitute proof. We don't have effective ways of discussing ambiguous findings without immediately triggering polarization and controversy. Those are problems we need to solve, because this will happen again. The final analysis. So why have theories about 3I divided by Atlas spiraled so completely out of control? Because it represents a perfect storm of factors that generate uncontrolled speculation. It has multiple genuine anomalies that don't have easy explanations. That's the foundation. If 3I divided by Atlas were completely ordinary, there'd be nothing to talk about. It involves the possibility of alien technology, which triggers deep psychological responses. Humans are hardwired to detect agency and intelligence. We evolved to see patterns and infer intentions. When something seems anomalous, we naturally wonder if someone made it that way. It landed in a scientific community that's divided on how to handle anomalies. Some researchers want to explore speculative possibilities. Others want to maintain strict standards of evidence. Both approaches have merit, but their intention, creating conflict. It's being studied during the social media age when every claim and counterclaim gets amplified immediately. The traditional, slow, careful process of scientific debate has been accelerated and publicized in ways that exaggerate disagreements. It emerged at a time when public trust in institutions, including scientific institutions, is fragile. People are primed to believe either that the establishment is hiding something or that fringe researchers are spreading misinformation. Either narrative fits depending on your perspective. And finally, it's genuinely uncertain. We don't have enough data yet to resolve the questions definitively. That uncertainty leaves room for speculation to flourish. All of those factors together created the conditions for theories to spiral out of control. The scientific questions are real. The anomalies are documented. The debates are legitimate. But the public discourse has gotten ahead of the evidence. Claims that might have been presented tentatively in academic papers became definitive statements in headlines. Careful probability estimates became, Harvard scientist says it's aliens. Thought experiments became theories. That's not entirely anyone's fault. It's an emergent property of how information flows in our current media ecosystem. But it's also not entirely helpful, because the real story of 3I divided by Atlas is interesting enough without the hype. We've encountered an interstellar visitor with properties unlike anything we've seen before. It's challenging our models. It's forcing us to think about how comets form in different stellar environments. It's providing data about the early galaxy and the diversity of planetary systems. That's exciting. That's worth paying attention to. Whether it's natural or artificial almost doesn't matter at this point. Either way, it's teaching us something new about the universe. If it's natural, we're learning that interstellar comets are far more diverse than we thought. That chemistry and composition can vary enormously depending on where and when an object formed. That we need better models that account for the full range of stellar environments across the galaxy's history. If it's artificial, well, that would change everything. But let's be honest, it's probably not. The most likely outcome is that 3I divided by Atlas is a weird comet. Genuinely unusual, statistically improbable, but ultimately natural. The size coincidence will turn out to be selection bias. The water emissions will be explained by unusual internal structure or composition. The nickel-iron ratio will reflect different formation chemistry. The trajectory will be a lucky alignment. The wow signal connection will be coincidence. The polarization will indicate unusual dust properties. Each anomaly will eventually get a natural explanation. Maybe not immediately. Maybe not until we've observed many more interstellar objects and can see the full range of variation. But eventually, and when that happens, the controversy will be forgotten. 3I divided by Atlas will become a footnote. An interesting case study about how science sometimes struggles with ambiguous data. A cautionary tale about letting speculation run ahead of evidence. But for now, in this moment, it remains unresolved. The theories continue to spiral. Scientists continue to argue. Media continues to speculate. And somewhere out in space, beyond the orbit of Jupiter, a 5-kilometer chunk of ice and rock and dust that's been traveling through the void for billions of years continues its journey through our solar system, oblivious to all the human drama it's created, oblivious to the fights it's caused, oblivious to the theories swirling around it. It's just doing what interstellar objects do, passing through. A brief visitor from the vast darkness between the stars. Whether it's a natural comet carrying chemistry from the early galaxy, or something more deliberately sent to study our solar system, or something in between that we don't yet have concepts to describe, one thing is certain. 3I divided by Atlas has shown us that the universe still has the power to surprise us, to challenge our assumptions, to make us question what we think we know. And in the end, maybe that's the most important lesson. Not the specific answers about this one object, but the reminder that we're still at the very beginning of understanding what's actually out there. We've explored a tiny fraction of the cosmos. We've studied a handful of interstellar objects. We've searched for alien signals for a few decades in a universe that's billions of years old. The fact that we don't have all the answers about 3I divided by Atlas isn't a failure. It's a sign that we're pushing the boundaries of our knowledge, that we're encountering things we haven't seen before. That's what exploration looks like. It's messy, uncertain, controversial, but it's how we learn, how we grow, how we expand our understanding of reality. So yes, theories about 3I divided by Atlas have spiraled out of control. Yes, the speculation has exceeded the evidence. Yes, scientists are fighting about it in ways that aren't entirely productive. But underneath all that noise, something remarkable is happening. We're collectively wrestling with genuine cosmic mysteries. We're trying to figure out what this strange visitor means. We're thinking seriously about our place in the universe and whether we're alone. Those are questions worth asking, even if we don't like the answers, even if the process is uncomfortable, because that's what it means to be human, to look up at the stars and wonder, to see something we don't understand and try to figure it out. To disagree passionately about what the evidence means while still working toward truth. 3I divided by Atlas will eventually reveal its secrets. The observations from JUICE and Juno will provide new data. The scientific debates will continue. Eventually, a consensus will emerge about what this object really is. Until then, we're left with uncertainty, with competing theories, with spiraling speculation. And maybe that's okay. Maybe the uncertainty is part of the story. The moment before we know, when anything still seems possible, that moment won't last forever. But while it does, it's giving us a glimpse of how humanity handles genuine cosmic ambiguity. For better or worse, this is us. This is how we respond when the universe shows us something we can't immediately explain. We debate, we speculate, we fight, we theorize, and eventually, slowly, stumbling forward through disagreement and confusion and controversy, we figure it out. That's the scientific process. That's human nature. And that's why theories about 3I divided by Atlas are spiraling out of control. Not because of any single factor, but because of all of them together. The genuine mysteries, the human psychology, the institutional dynamics, the media amplification, the philosophical questions, all swirling around one object that might be completely natural, might be something unprecedented, or might be something we don't yet have the framework to understand. Time will tell. The data will accumulate. The truth will emerge. Until then, the theories will keep spiraling. The debates will continue. And somewhere out there, 3I divided by Atlas keeps moving through the darkness, carrying whatever secrets it holds deeper into our solar system. The most mysterious interstellar visitor we've ever encountered. And maybe, just maybe, the beginning of a much larger conversation about what's really out there in the vast cosmic ocean. If this story fascinated you, there's another cosmic mystery we need to talk about that makes 3I divided by Atlas look simple by comparison. Check it out next.